All right, so this is going to go through kinetic and potential energy, just our introduction to those concepts. You've learned them before, definitely. We're going to go into a little bit more detail with them, as well as understanding some of the math and the equations that support this idea of kinetic and potential energy. So first off, energy is going to be stored into two main types of energies. The first one is potential, which a potential energy is going to be based on something's position. We typically think of it as stored energies, right? So we think about this boulder having a potential. Well, also this spring here, because it's been compressed, also has a potential for something to happen, right? So potential means because of where it is, because of its position, something could happen from that. So other forms of potential energy, we think about this wrecking ball here. It has potential energy because it's swung backwards and it has the ability to then go and hit something swinging the other way. A bow and arrow has elastic potential energy because we've stretched the bow, that when we let go, because of its position, it will cause the arrow to go flying. And someone on a swing has a changing gravitational potential energy, right? The higher you go on the swing, the faster you're going to go. So your position definitely impacts what your experience is going to be like. All right? So gravitational potential energy is the equation mgh. It's based off of an object's height. So when we are calculating gravitational potential energy, we're going to use m, which stands for mass, g, which stands for the gravitational acceleration, which is the same for everything on Earth. So we'll see that here in a second for an example. And then h is the object's height above a certain position. So think about this, and I say that above a certain position because it's not necessarily always above the ground. If something is sitting on the table, this box right here maybe is sitting on a table, and you might not really think of it as having the potential to do anything. But if we're holding it above the ground, it definitely does at that same height. So think about it this way. So you have a spoon that is sitting on the table, and that table is 1.2 meters above the ground. We're going to find the gravitational potential energy of the spoon relative to the ground. So we're going to say the ground here is my zero. So my blue line here is my zero position, zero height, essentially. What it's going to look like is my equation is mgh. My mass is 0.03. Gravitational acceleration is 10. That's the same for everything on Earth, always going to be a 10. And then the height is 1.2, which that's going to give you a potential energy of 0.36 joules. We measure energy in something called joules. Now, let's take that same problem, but let's say that our zero height is the table, right? So find the gravitational potential energy of the spoon relative to the table. Well, relative to the table, the height is zero. So the mass doesn't change, gravity doesn't change, but because my height is zero, and anything ever multiplied by zero is always zero. So the potential energy there is zero based upon where we're measuring the height from, right? So this is kind of funky about energy. It can change based on where our zero position is or where we're measuring the height from, all right? So kinetic energy. So the other form of energies that we're going to talk about is kinetic energy. It's based on the motion of an object. The kinetic energy of an object we measure and calculate as 1/2 mv squared. All right? This is basically when something is moving, when a car is driving, where an arrow is going through the air. If it has a velocity, it has kinetic energy. Right? So kinetic energy, if we think about the math behind it, right? So imagine we have two bullets. One has a mass of 3 grams, this one right here. Another one has a mass of 6 grams. Both are fired with the speed of 40 meters per second. Which bullet has more kinetic energy and why? So what I said that the kinetic energy is based on velocity and mass, right? It's 1/2 mv squared. Because they both have the same velocity, the larger bullet will have more kinetic energy because it has a bigger mass. Now, we're going to prove this with math, excuse me. The kinetic energy of the big bullet, right, is 1/2 mv squared. So it's 1/2 times the mass, 0.006, times 40 squared, which is actually going to give me 4.8. Now, this, I know it's given in grams, 3 and 6, but it should be measured in kilograms, so that's why it's converted here. The kinetic energy of the small bullet is 1/2 mv squared. It's 1/2, and the only thing that's different is this is a half the size of this number, so calculating that out, we get half the energy. We could also find the speed of something if we know its energy, and this is going to be helpful when we talk about conservation of energy and why this kind of makes sense, right? So what is the speed of a 0.145 kilogram baseball if it has a kinetic energy of 109 joules? Well, if we plug that into my equation, 109 equals 1/2 0.145 v squared. Then what I need to do is I need to get v by itself. So here's the process to do that. The first thing I'm going to do is I'm going to multiply 1/2 times 0.145, and I get 0.0725. And then I'm going to get that value over to the other side. I'm going to get v by itself. So I'm going to divide 0.0725. So I get 109 divided by 0.0725, and that gives me 1,503. Now, I don't want v squared, I want v. So to get rid of the v squared, sorry, I couldn't find the function for it, but I need to take the square root of that value. And if I take the square root of that value, 1,503, I should get a value of 38.8, 38.77, 38.8. All right. So how could this baseball actually have more kinetic energy? Could it do? Well, there's two main ways. The baseball could either have a bigger mass, or it could have a higher velocity. Either of those two ways is going to give you more kinetic energy. All right, so let's do some quick concept questions, and then we'll be done with this. So what is true about the potential energy of a skydiver falling at terminal velocity? Well, the correct answer is it's going to decrease. It's going to decrease because its height is decreasing, so the potential energy is decreasing as well. What is true about the kinetic energy of a skydiver falling at terminal velocity? So kinetic energy now. Similar question, but now we're talking about kinetic energy. Yeah, so this is one of those funky situations. There we go. Is that this one actually remains constant, and it's falling at a terminal velocity, and that means that it's not speeding up, it's not slowing down, it's staying at the same speed. So that means that the net force on it is 0, and if it's staying at the same speed, that means its kinetic energy is going to stay the same. So the air resistance in this case has equaled the force of gravity. How does the potential energy change when you double your height? Well, the potential energy is going to double, and that's because mgh. If this is 1 times 1 times 1, if we have it 1 times 1 times 2, we just doubled it, right? So doubling the height actually doubles your potential energy. Doubling the mass also doubles your potential energy. How does the kinetic energy change when you double your velocity? Now, be careful with this one, and I have the equation here, 1/2 mv squared, right? This one's a little tricky. The correct answer is actually it quadruples, and here's why. If I take v and make it from 1 to 2, 1 squared is 1, 2 squared is 4, right? So that's actually 4 times, that's quadruples what it originally was. If I double the mass, it only doubles the kinetic energy, but if I double the velocity, it actually quadruples it. All right, so that's a quick overview of kinetic and potential energy. We'll go into a little bit more detail of these. They should be somewhat review in terms of the ideas. The math is really the big thing that's new for you guys.